Hi everyone, my name is Dakai Kang. I'm currently a 30 PhD student at UC Davis. In this video, I will present my latest academic paper, HotStuff-1, Linear Consensus with One-Phase Speculation. This paper has been accepted by SIGMOD'2025, and it was co-authored by me and three professors, Professor Suyash Gupta, Professor Dahlia Malkhi, and Professor Mohammad Sadoghi. In recent years, in the area of binding fault tolerance protocols, a protocol named HotStuff has catched people's attention. HotStuff is a Byzantine fault tolerance consensus protocol that achieves safety and liveness through a three-phase commit phase, and it supports linear message complexity. HotStuff with N replicas can tolerate at most F Byzantine replicas. The Byzantine replicas can have arbitrary malicious behaviors trying to break the consensus in the system, but the consensus can be guaranteed by HotStuff as long as n is larger than 3f. HotStuff has three main phases: prepare, pre-commit, and commit. In each phase, the leader broadcasts a message, and all replicas will send the votes for the message back to the leader. The leader then collects n-f of the votes to form a quorum certificate, and then broadcasts the certificate in the next phase. After three phases like this, a commit certificate can be formed and received by all replicas. After receiving the commit certificate, the replicas will commit and execute the transaction and send responses back to the clients. Then the replicas will move to the next wheel with a new leader, and in HotStuff-1, the leaders are rotated in a round-robin way. So to boost the throughput, HotStuff has an optimization. It has a streamlined version that overlaps phases of consecutive transactions. As shown here, after each phase, the leader is rotated, and the votes are sent and collected by the subsequent leaders. And the phases of the consecutive transactions are overlapped. For example, here in view 2, the commit phase of transaction T0 at the same time is the pre-commit phase of T1, and it is also the prepare phase of T2. The streamlined version, such an optimization increases system throughput and has been widely adopted by other HotStuff family protocols. Though HotStuff has been very successful in recent years, it faces some challenges. First, HotStuff has a very high latency. In HotStuff, it takes 4 broadcast steps and 3 vote steps to commit a proposal. While in PPFT, which is another successful protocol that requires quadratic message complexity, it only takes 1 broadcast step and 2 output steps to commit a proposal. So the challenge is, can we reduce the latency of HotStuff? One protocol that was proposed trying to reduce the latency of HotStuff was HotStuff-2. This is the workflow chart of HotStuff-2. In HotStuff-2, a replica locks on the transaction after receiving its prepare certificate, and the replica commits the transaction after receiving its commit certificate. In total, HotStuff-2 has 3 broadcast steps and 2 vote steps, so HotStuff-2 has a lower latency than the original HotStuff. Besides the high latency, HotStuff faces other challenges. The performance of HotStuff can be greatly negatively affected by the slow leaders. Some leaders might be slow because they have low computational capacity, and some leaders might be intentionally slow. They are slow on purpose because they want to delay their proposals until the end of the timer to get the maximal extractable value from their transactions. The leader slowness problem can cause a low throughput in HotStuff. This is an example about how these slow leaders can negatively affect the performance of HotStuff. Here, we assume the timer length of each wheel is 3 seconds, and the average time for an honest leader to commit a transaction is 1 second. If all the leaders are honest, the system will behave like this, and the throughput would be 1 transaction per second. However, if we have one slow leader R1 who intentionally delays its proposal for the MEV, then the system will act like this. As we can see here, T1 and T5 proposed by the slow leader R1 have to go through a 2-second delay before being proposed, and the system throughput will drop from 1 transaction per second to 0.67 transaction per second. The third challenge in HotStuff is that the streamlined version of HotStuff is vulnerable to an attack called tail forking attack. On the tail forking attacks, proposals from honest leaders can be intentionally ignored by subsequent malicious leaders, even if all replicas have voted for them in the previous wheel. The tail forking attacks not only lead to a low system throughput, but also lead to an unfair situation for the victim honest leaders. And here is an example showing how the tail forking attacks can affect the performance of HotStuff. Again, we show how the system works when all leaders are well behaved. As you can see here, no transactions can be skipped, all of them are chained together, and all of them will be committed. However, this is when we have a Byzantine leader R2. Now, the transaction blocks from R1 are all intentionally ignored by R2, and R2 can simply claim that it did not receive enough votes to form certificates for transaction T1 and T5. Though the transactions T1 and T5 from R1 are intentionally ignored by R2, the honest replicas have no ability to question the behavior of R2. The victim leader R1 can do nothing to protect itself. Now let's see how we resolve the challenges mentioned above. To reduce latency, we use speculation to go one step further than HotStuff-2. We allow replicas to speculatively execute transactions, reducing the latency for one more phase. And to mitigate the impacts of slow leaders and the tail forking attacks, we introduced a mechanism called slotting. The slotting mechanism allows leaders to propose as many slots as possible before their timers are out, 1 transaction per slot. With the speculation mechanism and slotting mechanism, we get our protocol HotStuff-1. HotStuff-1, it ensures linear complexity as HotStuff and HotStuff-2, and it is also the first HotStuff family protocol that employs speculation. Also, HotStuff-1, it is resilient against the leader slowness problem and the tail forking attacks because of the slotting mechanism. So now let's look at the speculation part. Let's look at the details. HotStuff-1 is designed based on HotStuff-2. Let's see what the difference is between them. In HotStuff-1, it has the same phase number as HotStuff-2. However, instead of sending responses to the clients after receiving a commit certificate, replicas speculatively execute a transaction and send responses back to the clients after receiving a prepared certificate for it. And when the commit certificate is formed and received, replicas will now send more responses to the client. So in HotStuff-1, responses are sent one phase earlier than in HotStuff-2, which further reduces the latency. However, introducing speculation is not something straightforward. It could probably bring some safety issues. First, speculative responses are not real responses. They are more like prepair votes rather than commit votes in the system. Thus, in HotStuff-1, we should require the clients to collect 2 F+1 speculative responses rather than F+1 as in previous works. Second, we found a prefix speculation dilemma when we tried to introduce speculation into HotStuff-2. After sending a speculative response for transaction T, a replica might still switch to vote for a conflicting branch later, even if the replica is honest. Such a behavior will invalidate the previous speculative responses. So, a client, it might mistakenly collect 2i+1 invalid speculative responses, and it might mistakenly consider that one of its transaction has been committed, but actually it did not get committed. So this is something that is unsafe for the clients. So how to save this problem? The replicas must be very, very careful when they want to speculate on something. So in our paper, we have designed 2 rules for the replicas to follow when they want to speculate on some transactions. The first rule is called a prefix speculation rule. It requires that when a replica R wants to speculate on transaction T, it has to make sure the prefix of transaction T has been committed. The other rule is called no-gap rule. It requires that if R wants to speculate on a transaction T that was proposed in view V, R must have received the prepared certificate of transaction T exactly in view V. So here are some illustration examples that can help you understand this. Now replica R had received a prepared certificate for transaction T1. The certificate is P1. And the prefix speculation rule requires R to check if the prefix of T1, which is T0, has been committed. If T0 is not committed, then the rule is not satisfied. So we cannot speculate. But if T0 is committed, then the prefix speculation rule is satisfied. However, only satisfying one rule is not enough. We also need to check how the replica R received the certificate P1 to see if the no-gap rule is satisfied. If R received P1 from a proposed message in view 2, then the no-gap rule is not satisfied according to its definition. However, if replica R received P1 from a prepared message in view 1, then the no-gap rule is satisfied according to the definition. If both of the rules are satisfied, then it would be safe to speculate on a transaction. In our paper in the extended report, we have proved that with these 2 rules, it will be always safe for replica to speculate on some transactions. And we have also provided more detailed examples about the prefix speculation dilemma in the appendix of our extended report. The extended report is available on arXiv, and here is the link. Next, let's talk about the slotting mechanism. With the slotting mechanism, we allow a fast leader to propose as many transactions as possible before its timer is out. So you can see that here we form a chain that looks like this. And when constructing such a chain, we have one requirement. That is, a leader cannot propose its next slot until the certificate for its current slot has been formed. It means that each slot here must contain the certificate for the previous slot in the same view. That is, the slot S in view V, denoted as TVS, must contain the certificate PVS-1, which is the certificate for slot S-1 in view V. Such a requirement holds true for all slots except the first one in each view. Now let's see how this slotting mechanism can reduce the impact of slow leaders. Without slotting mechanism, the system will act like this when there is a slow leader R1. With the slotting mechanism, the system will act like this. Each honest replica can propose 3 slots when it is the leader, and the throughput can increase to 0.83 transactions per second. So, slotting mechanism makes the system more resilient to the influences of the slow leaders. Now let's see how does the slotting mechanism help with the tail forking attacks. With the slotting mechanism, the certificate of slot S in view V, PVS, implies that at least F+1 honest replicas have locked on the certificate of the previous slot, PVS-1. So in the next view, if the leader wants to tail fork multiple slots, the proposal from the new leader will not be accepted by at least F+1 honest replicas, so it cannot form a certificate and its proposal will not be valid. Thus, in each view, at most one slot can be tail forked. Here is an example. In this example, the leader 0 has proposed 4 slots, and the leader 1 is a Byzantine leader, and it wants to tail fork the slots in view 0. The certificate for the last slot has been formed, so it means that at least F honest replicas have locked on the second last slot of view 0. Now, leader 1, it can only tail fork the last slot, but it cannot ignore any other slots in view 0. So with the slotting mechanism, as long as an honest leader can propose multiple slots per view, it does not need to worry that its proposals will all be intentionally ignored, will all be tail forked by the subsequent malicious leaders. Now let's look at the performance results of HotStuff-1. So first, we compared the scalability of HotStuff-1 with the previous works. We tested their performance with a varying number of replicas. We can see that whatever the number of the replicas is, HotStuff-1 exhibits the same throughput as the other protocols, and it has the lowest latency. It has the best performance no matter it has the slotting mechanism or not. We also tested their scalability in a geoscale setting with the standard TPCC benchmark. Again, HotStuff-1, it exhibits the same throughput as other protocols, and it has the lowest latency among them. Next, we tested their performance on the unfavorable network conditions. To simulate the unfavorable conditions, we injected a 500 millisecond network delay to some of the replicas. The results show that HotStuff-1 with the slotting mechanism exhibits the best resilience against these unfavorable conditions. It has the highest throughput and the lowest latency among all these protocols. This is because the slotting mechanism enables the unaffected fast leaders to propose more slots in their views, mitigating the low performance caused by the impact replicas. Next, we tested their performance on the different types of attacks, such as tail forking and the slow leaders. The results show that HotStuff-1 with slotting has better resilience against these attacks than the protocols without slottings. HotStuff-1 with slotting, it can maintain the high throughput and low latency when the attacks happen. Such a performance is consistent with our claims mentioned above. So in conclusion, HotStuff-1 employs speculative execution to offer consensus with low latency in one single phase. And HotStuff-1 with slotting can protect the performance against the leader slowness problem and the tail forking attacks. And that's all about our presentation related to HotStuff-1. If you want more information, if you want to read more published work from us, you can scan the QR codes of our website. Thank you very much.